Imagine waking up to blaring news alerts. Your heart races. The headlines scream the unthinkable. A black hole is hurtling towards Earth. Panic engulfs the planet. This isn't science fiction. It's a cosmic nightmare come to life. We've always marveled at the vastness of space, the mysteries it holds. Now, one of those mysteries is knocking on our door, threatening to swallow our world whole. We humans, a species that built its civilization on gazing at the stars, now find ourselves staring into the abyss. What do? Surrender to the inevitable, or fight back against a force that seems unstoppable? The answer, as with most things cosmic, is far from simple. But one thing is clear: our understanding of the universe is about to be tested like never before. We stand at the edge of the unknown, staring down a cosmic beast that defies our comprehension. The very laws of physics seem to crumble in the face of a black hole's overwhelming gravity. Yet in the face of this existential threat, the human spirit refuses to back down. We will explore every possibility, challenge every assumption, and seek out any glimmer of hope, no matter how small. For the first time in our history, the survival of humanity hinges on unraveling the secrets of the most extreme objects in the universe. The clock is ticking, and the stakes have never been higher. Welcome to the ultimate battle for survival. Our instincts scream for a solution, a way to fight back against the unknown and the terrifying. Our history is filled with battling threats, both terrestrial and extraterrestrial. From the earliest days of space exploration, humanity has always sought to conquer the unknown. But how do you fight an enemy that can devour planets whole, an entity so powerful that it bends the very fabric of reality? Could our most powerful weapons, the ones we reserve for only the direst situations, offer any hope? Could the sheer force of a nuclear explosion make a difference? Imagine launching all our nuclear weapons at the black hole. Would the combined might of our arsenals be enough to make a dent? The short answer is, it wouldn't work. The laws of physics are not on our side in this battle. In fact, it might even make things worse. The energy from the explosion would be absorbed, potentially increasing the black hole's mass. You see, black holes aren't like planets or stars, solid objects we can blast into oblivion. They are far more complex and enigmatic. They're regions of space-time so dense that nothing, not even light, can escape their gravitational pull. Their gravity is so intense that it warps space and time around them. Imagine throwing a pebble at a bottomless pit. No matter how hard you throw, it will never fill the void. Now imagine that pit being a black hole and the pebble being a nuclear bomb. The bomb would simply disappear into the abyss, leaving no trace. You begin to grasp the futility of the situation. The scale and nature of a black hole are beyond our conventional means of attack. Detonating a nuclear weapon near a black hole would be like throwing a firecracker into a supernova, a spectacular but utterly insignificant event. The explosion would be swallowed whole. The immense energy released by the explosion would simply be absorbed by the black hole, adding to its already formidable mass. Instead of harming it, we would be feeding it. It's like trying to extinguish a fire with gasoline. The more energy we throw at it, the stronger it becomes. To understand why this is the case, we need to delve deeper into the nature of black holes themselves. These are not just dense objects. They are cosmic phenomena that challenge our understanding of the universe. These cosmic monsters are not simply dense objects. They represent a fundamental breakdown of our understanding of physics. They are places where the known laws of physics cease to apply. They are regions where gravity reigns supreme, warping the fabric of space-time to an unimaginable degree. The closer you get, the stronger the gravitational pull becomes. So, if brute force won't work, what other options do we have? How can we confront something that defies our conventional understanding? To answer that, we need to think outside the box, beyond the realm of conventional weaponry and into the realm of theoretical physics. Perhaps the key lies in understanding and manipulating the very fabric of space-time itself. Before we can hope to conquer our cosmic adversary, we need to unravel its mysteries. A black hole isn't a hole in the traditional sense, but rather a region of space-time where gravity is so overpowering that nothing can escape. Picture a place where matter is compressed into an infinitely small point, creating a gravitational pull so intense that it distorts the very fabric of space-time. This point of infinite density is known as a singularity. Encircling it is an invisible boundary called the event horizon. Cross the event horizon and you're on a one-way journey to oblivion. Not even light, the fastest entity in the universe, can escape the grip of a black hole once it crosses this point of no return. Black holes are born when massive stars die and collapse under their own gravity. Imagine the mass of several suns compressed into a region the size of a city. That's the kind of extreme density we're dealing with. Now envision this cosmic titan hurtling towards our planet. It wouldn't be a collision in the usual sense. Instead, Earth would be gradually stretched and torn apart by the black hole's immense tidal forces. A process known as spaghettification. It's a grim fate, but understanding the science behind it is crucial if we ever hope to find a way out of this predicament. So we can't nuke a black hole. It's time to explore more radical, more imaginative solutions that might seem like science fiction, but in the face of such a cosmic threat might be our only hope. The accretion disk, a swirling mass of matter, forms around the event horizon. This disk is composed of gas, dust, and other stellar debris that gets heated to extreme temperatures as it spirals inward. Sometimes black holes can also emit powerful jets of particles that shoot out at nearly the speed of light, a phenomenon that still puzzles scientists. When two black holes merge, they create ripples in space-time known as gravitational waves. These waves were first detected by the LIGO Observatory in 2015, opening a new window into the universe. Observing black holes is a challenge because they emit no light. Scientists rely on indirect methods, such as observing the behavior of nearby stars and gas, to infer their presence. Supermassive black holes, millions to billions of times the mass of our Sun, reside at the centers of most galaxies, including our own Milky Way. They play a crucial role in the formation and evolution of galaxies. Future missions aim to study black holes up close, using advanced technology to gather more data and perhaps unlock the secrets of these enigmatic objects. By running complex simulations and models, scientists hope to better understand the physics of black holes and their impact on the cosmos. The immense gravitational pull of black holes affects everything around them, from the orbits of stars to the flow of time itself. Understanding these effects is key to unlocking the mysteries of the universe. The event horizon marks the boundary beyond which nothing can return. It's a point of no return, a concept that challenges our understanding of physics and reality. At the heart of a black hole lies the singularity, a point where our current understanding of physics breaks down. It's a place where the known laws of nature cease to apply, and new theories are needed to explain what happens there. The influence of a black hole extends far beyond its event horizon, warping space-time and affecting the motion of objects in its vicinity. This warping can create gravitational lensing, where light from distant stars is bent around the black hole, creating distorted and magnified images. Black holes have a life cycle, from their formation in the death throes of massive stars to their eventual evaporation through a process known as Hawking radiation. This radiation, predicted by physicist Stephen Hawking, suggests that black holes can slowly lose mass and energy over time, eventually disappearing completely. Black holes are not just cosmic destroyers, they also play a vital role in the universe. They help regulate the growth of galaxies, influence the formation of stars, and provide a unique laboratory for testing the laws of physics under extreme conditions. Despite decades of research, black holes remain one of the greatest mysteries of the cosmos. They challenge our understanding of space, time, and the fundamental nature of reality. As we continue to explore and study these enigmatic objects, we may one day unlock the secrets they hold and gain a deeper understanding of the universe itself. If a black hole is fueled by matter, could we use its cosmic nemesis, antimatter, to neutralize it? This tantalizing question has captivated scientists and science fiction enthusiasts for decades. Antimatter, the mirror image of ordinary matter, annihilates upon contact, unleashing a colossal amount of energy. This annihilation process is one of the most efficient energy releases known to science. It's the stuff of science fiction, but could it be the key to our cosmic salvation? The idea of using antimatter to combat a black hole is both thrilling and daunting. Picture this: creating an antimatter black hole, a mirror image of the one threatening our existence. This antimatter black hole would theoretically have the same properties, but opposite charges. In theory, when these two cosmic titans collide, they would annihilate each other in a spectacular release of energy, potentially saving our planet. The collision would be a cosmic event of unprecedented scale. It's a captivating idea, but the reality is far more complex. The challenges we face in making this a reality are numerous and formidable. Firstly, creating even a tiny amount of antimatter requires unimaginable amounts of energy. Current technology, such as particle accelerators, can only produce minute quantities of antimatter at an enormous cost. We're talking about harnessing the power of entire stars, a feat far beyond our current technological capabilities. The energy requirements are astronomical, making this an almost insurmountable challenge. Secondly, even if we could create an antimatter black hole, getting it to collide with the real one would be like threading a cosmic needle. The precision needed for such an alignment is beyond our current understanding and control of cosmic events. The slightest miscalculation, and we'd end up with 2 black holes instead of none, doubling our troubles. This could lead to an even greater cosmic disaster with unpredictable consequences. Furthermore, there's no guarantee that the annihilation of a black hole and its antimatter counterpart would completely neutralize the threat. The interaction between such massive entities could have unforeseen effects. The energy released from such an event could be even more destructive than the black hole itself, bathing our galaxy in deadly radiation. This radiation could have catastrophic effects on all forms of life. So, while the idea of fighting fire with fire, or rather black hole with antimatter black hole, is intriguing, it's ultimately a dead end. The risks and challenges far outweigh the potential benefits. We need to explore other avenues, other theoretical possibilities that might offer a fighting chance against this cosmic leviathan. The universe is vast and full of mysteries, and perhaps the solution lies in an area we have yet to discover.